So, thank you, thank you. Yeah, so my name is Zakarias Nordfaldt. I originally come from Sweden, but I've been living here now the last 4 years in the Netherlands. And yeah, like the introduction here, I'll be talking about HitWizard, and that's a program predicting the chance of a song becoming a hit next week. So I come from the company Goldmund, Wyldebeast Wunderliebe. I'm a developer there, and they are stationed both here in Groningen and in Amsterdam. Probably some of you already know them. So let's get started. This is what my talk will be about. First I will have a little introductory, like about music and what makes a hit, and some machine learning, and then dig into a little more of how the HitWizard is built with classification, some general, and the two main algorithms that I've used or we've used in HitWizard, pre-processing results, and how it could be improved in the future. So first, this song, Shape of You from Ed Sheeran, probably all of you in here know. And if you don't, it's a hit song for sure. It's on the top list on all charts. It's being played on the radio all the time, and it has been for quite some time now, and probably it will keep on for a little while longer. So this song will keep on recurring in the rest of my talk, so that's why I wanted to show it here in the beginning as well. I'll be using it as an example. So first of all, let's discuss what is a hit song. A hit song, the definition is a little hard. We have charts, and we have different ways of measuring the songs that are the best at the moment. We also have experts saying, okay, this song is good, this song is bad. And but we don't have like one tool saying, okay, this is a hit. And there's a lot of money in the music industry going into producing hit songs. We have production, PR, management, labels, and all that. You all know it's a big industry. And there is a big need of these kind of tools that you can see. Okay, is a song doing good? Is it becoming a hit? Is it better than the competitors? Both for the artist himself and also for other labels and stuff to see where they're spending their money, if it's for a good cause. So that's why there's a machine learning algorithm that can manage to predict or create a classifier that can predict something like this can be a very good thing. So here we're coming into the machine learning. So now we want to make a program that can do this in a general case, that they compare all songs on the same manner. So it can give it a result, and then you can compare it between the songs. And also, in order to do this, we need to have a target. We need to say, okay, what is a hit? So that we can say, okay, this machine did it correctly, or this program correctly classified as a hit, yes or no. And for that, we're now using the Spotify top 200 charts. And I think they give a pretty good picture that if a song is in the Spotify top 200, then it's quite a hit. Maybe not everyone agrees, but that's the target we've used for this HitWizard anyway. Yeah, so HitWizard. Let's dig into a little more now about classification. I'm just going to give a general introduction to classification for those of you who don't really know what it is. Classification is we want to classify something as being, in this example, we want to classify a picture as being either a cat or a dog, or it can be true or false, or it can be a multiple options. But for this example, we're taking cats and dogs. It's quite simple. We have a picture. We want to say, is this a cat, yes or no, or is it a cat or a dog? And in order to do that, we need to train a classifier. To train a classifier, we in the general case now, we train the classifier by feeding it a large amount of pictures, and then giving it feedback saying if it is correct or not. And every time, in every iteration, we give it a new picture. We let it adjust some values, adjust some weights and things like that. And it keeps on adjusting them using an algorithm, mathematics, in order to get a better result at every iteration. And eventually you have a trained classifier that can give a pretty good result, or hopefully a very good result. So let's dig into more how this works. And let's assume now that all cats are blue and all dogs are yellow. And for the sake of argument, let's say we have 1,000 pictures of cats or dogs that we can use for training. We already know if these pictures are a cat or a dog. So we just feed it one picture at a time, and it first will answer just in the beginning, it will be stupid. It will say, okay, this is a picture of a cat, and then we say, you were right or you were wrong. And if it was right, we continue with the next picture, and it remembers that it was right with those parameters. And the next picture, maybe it's wrong, and it will adjust the parameters a little, keeping in mind the previous pictures and how it has adjusted previously. So when you come up in larger numbers of training data, it remembers how it has been adjusting, and it remembers the features that were good for when it was correct, and that way it can kind of build up weights that are good. And in this case, we can see that the color is very distinct difference. And if we assume that all cats are blue, all dogs are yellow, the weight on the color will be very big, and we can easily see that if we get a new picture and the picture is blue, then it will be classified as a cat right away. So now let's go into two specific classification algorithms: support vector machines and neural networks. I used both of them in HitWizard, and we tested them against each other to see which one was actually getting the best predictions. And let's start with just looking at support vector machines. And then I'll soon say why we chose for the one we did. So we have a support vector machine. It's actually just a graph with two vectors, and we have the features on the axis. So on this y-axis, we get, or x2 in this case, we have the color of the animal. So maybe light at the top and dark at the bottom. And on this axis, we can have the hair length. So long hair, short hair. And then we start feeding it pictures, and it will place everything, but depending on these two features, on the graph. And then we will end up with having, in the case of cats and dogs, being very distinct with color. We can say that everything with long hair and dark is down here, and then everything with short hair and a light color ends up at that corner. And then that way you get like a separation, and if all dogs are dark-haired and dark color and short-haired, they will all end up there, and cats will end up there. Then when you take and then you have this graph, and then you use the algorithms for support vector machine, and you get this hyperplane in the middle, and that plane is made to separate the two clusters of cats and dogs as much as possible by creating as big length or as big a margin as possible between the outliers of the two groups. And that, when you then put in a new picture, it will also end up on the graph, and then you can immediately say if it's on that side of the plane, it's a cat, and if it's on that side, it's a dog. This is the basics, but then obviously we have more features than this, and we won't be able in real life to tell if a picture of a cat or a dog is a cat or a dog on just two axes with two features. So what you do then is you add dimensions. So here we've added another axis, so another feature, and instead of having a line now, we have a plane. And this way we can do even more separation. And this 3 vectors is about as much as we can picture on a picture and imagine, but in mathematics you can add n dimensions, and that way you can add more features. So that's the basics of support vector machines, and let's go into neural networks, and then I'll compare them soon. So a neural network is a different type of classifying, and it's based on how we classify or how we train our brains. So this is actually not a neural network, but an artificial neural network. And what we do is we have these neurons. In our brain, these are neurons, but in the artificial neural network, they are nodes. Let's call them nodes. So you have input nodes here, you have some hidden layer here that performs some magic, and then you have output there. The input, in the case of now predicting hit songs, will then be radio stations. It will be the amount of streams it has on Spotify. It will be, and on radio stations. It will be the audio features of the song, kind of identifying the song. And all of those will get a separate node. And then eventually, and the output, we get the value between 0 and 1. And this value will then represent if it's true or false. So above a 0.5, it will be true, and below it will be false. Every input, as you can see, also has a value. And then what happens in the middle, that's where the magic happens, and that's where actually the classification starts. So what we do is we assign weights to every one of these lines. And these weights, in the beginning, they will be stupid because the network is not trained yet. So we just assign, let's just randomly assign weights now. And then we have that first node, the value inside there, so the value of the feature, will be multiplied with every of these outgoing nodes to give a new value in the middle. The value in the middle would be then an average for all of these input nodes. And then it will happen once again, going and giving a final output there. So this is just a multiplication. And then the first time we will get an output and we will tell the network if it was correct, yes or no. And then while keeping on iterating, this network will then adjust these weights. And that's where the magic happens. And that's called backwards propagation. And I'm not going to dig into all about how that works now, because that's quite complicated math, and there can be all kinds of different algorithms you can use for adjusting them as well. But the key idea is, like I said a little earlier, that it remembers how it has adjusted, and it tries to adjust them to get a better output while still remembering what it has seen before, and what it has had correct and what it has had wrong. Eventually, you have weights on all of these, and on all of these, and then when you give it a new picture that it hasn't seen before, it calculates all of these values for the feature, it multiplies it, and it gives a result. And it turns out in neural networks that it's usually quite good, if you've trained them good. And this is the same way that our brain actually works when recognizing and learning to recognize stuff, but then instead with nodes, it uses neurons and electrons to do this same kind of calculations with feedback, learning what is what. So yeah, so first I just want to say that we chose for the neural network for the HitWizard. And the reason why we thought to support vector machine might be good is because hits are usually quite distinct. If you remember the graph, you have it's a graph, so you want to have them separated as much as possible. And now we're trying to separate the hit songs from non-hit songs. And when you think about it, hit songs can be, they usually get played a lot more than a non-hit song. And we were thinking that maybe features are actually that distinct from hit songs that you can separate them and get a good result with support vector machine. But then when in practice, when we were trying it, that was not really the case. And we did get better results with the neural network. And the main reason why we chose for it was because the results were better. The problem with the neural network is that you don't really know what's going on. So you get a result, but you cannot say that much about it. So back to Ed Sheeran Shape of You. These are the audio features for that song, and basically these features represent what that song is. For example, valence is a happy key feature of a song, and that's how happy it is. That's how they measure how happy a song is. All of these values will then become features, and but we can see that all of them cannot be used in the way they are right now, so something more has to be done first. We have to pre-process the data. And to pre-process the data is making it in the shape that you want to have so that you can just feed it to the network. Because a lot of the data can be wrong when you get it. You get it raw from, in our case, we're getting from RadioRadar. They're supplying us with radio broadcasts, and the audio features come from Spotify, and we have to combine all that and process it, and then eventually we have numbers that we can just give the nodes to do the calculation. So let's look at the data that we're using. We have about 2.5 million broadcasts from all Dutch radio stations. It can be good to mention that this HitWizard is done on the Dutch market, so it's predicting for the Netherlands. We are getting the audio features, the specifications for the song from Spotify. It's actually free to get for every song that's uploaded to Spotify. And we've been using IBM Bluemix, analyzing tool from IBM, in order to do some statistics and to get some more insight in the data before actually trying to classify it. This is also an important step when doing machine learning. You should not haste too much into actually doing the classification and training a classifier and pre-processing. But do some statistics, figure out, like, can you see already some patterns in the data? You have to decide on what algorithm to use, and there are a lot out there. And also doing this, you can find noise, you can find data that's just wrong, that has been recorded wrong, or you have received it wrong, and that will just mess up your result. So that has to be gone away. And you can also, in our case, we did some stuff, can be discussed if it's good or bad, but we assigned weights to the radio stations. And we also used that as a feature later on. And it turned out that it was giving quite a good result, but it can also be biased since we have done our statistics, and that way we have assigned those weights. Important point is that that was done now, but in a year, if this classifier is still used, it might be different. But we got a better result, so we decided to stick with that right now. And we also took away some stuff that were some radio stations, for example, that were just not good predictors at all, that were also generating a worse result. But this is also the same kind of argument as with the weights, that that's something that we decided now, and that radio station might be a great predictor in a few years. And maybe it's more up to the network to decide which radio station is good and bad, and not up to us. But since we were getting a better result, we still decided to stick with this. So here, let's go into some pre-processing. And so to give some examples, we cannot just feed this data like this, and we have an ID, and we have like for duration in minutes and seconds, and it has to be a value between 0 and 1. So what we need to do is we need to remove the data that we don't want, and we need to normalize it to have values between 0 and 1. So for example, ID is not necessary, we throw that one away. You can see here on the right side that all values have been normalized to be between 0 and 1, and that can be done with different algorithms, and there are things out there, great Python libraries, I will show a little soon. And also the duration has there also been become a number. This way they can make sense. And it's important to normalize the data that you train on with the exact same way as the data that you later classify. So from the songs that you have trained, you have to normalize in the same way as the song that you classify. So an interesting way is, or an interesting thing is with the categorical and ordinal data. We also have to normalize this, like the categorical in the sense of music, you have the genre, so rock, pop, dance. How do we put that on a scale? How do we give that a value? And ordinal data is data that can be ordered. So like, for example, grades in high school can be A, B, C, D. There you can easily say that maybe a A is 1, a B is 0.75, a C is 0.5. That way you've given them an order. But in genres, you cannot do that. They are, it's not possible to order them on a logical way. Pop is just as much worth as rock. We think anyway. So what we can do then is we can give them everyone a separate node. So every one of them become a separate feature, and we assign 0 to all of the ones that are irrelevant for that song, and a 1 at the one that is relevant. And that way we can let the network later on decide which ones of them are the most important. And unfortunately we don't know that in the result really, but that way the network can give a good prediction anyway. And that way we can use this data as well. So let's look in a little in Python how this was implemented. We're using Scikit Learn. It's a Python library which is quite good with doing predictions and training classifiers. And this is for training the neural network. What we do first is just read the input, the training data, storing it in a variable, and those are the first 4 lines. This 5th line in between training data equals filter input, that's just us removing some metadata that we added that's not necessary, so that line can be just ignored. And then we have the scalar. This is for the normalization. We create a standard scalar, and we fit it to the training data so that it matches the data and recognizes it. Then afterwards, we actually normalize it with this transform, creating all of these values between 0 and 1. And after that, we train a classifier with this second last line, and then we store the classifier and the scalar in a location. Important here to also store the scalar, because we will use it later on, as I said, when also classifying, then we have to use the same scalar. So here is when we actually classify a song to get the results. We load the model, the classifier that we stored, and the scalar. That 3rd line is the same, just removing some metadata. And then the 4th line is first normalizing it using this scalar with transform. and then the second last line is predicting the probability, and that's where we actually get the value between 0 and 1 of how big the probability is. In this Scikit Learn, when using it, you actually get two probabilities, probability of it being true and the probability of false. And the winner is the bigger. So this is actually the entire implementation of training and classifying using Scikit Learn. So that's actually a very small part of it. What you later on have to choose on is what algorithms you put in the actual network, the backwards propagation and those things, and that you have to do some analyzing and think about what will fit best in your data. Also do some testing to see where you get the best results. So let's go to the actual results of HitWizard that we got. First I want to just switch over here and I want to show you. So here we have the HitWizard, let's remove this. Let's put in the Ed Sheeran shape of you. So you can see there are quite some remixes as well. So this one has a 88.01% chance of being the chart next week. So this is now a live check. It's quite sure that it will be in the charts, but my guess would probably be yes as well, because it's like number 4 now, I think. And the chance is big that it will probably be there next week as well. Oh, like that, and then we're back. Okay, so that was just the one song we tested now, but obviously to see how good this classifier is doing, we need to try it on a loads of songs. We need to test it. What you usually do when you train a classifier is you split the data up in training and test. About 70% training, and that's what you use to train the classifier, and then the last 30% you use for testing. And the testing is also important just to see how good it is, how good your result is. And we tested on 100,000 unique lines, and this is the result that we were getting then. So those 100,000 were in October, November. We had 53% of the hit songs we predicted correctly, and 99% of the non-hit songs we predicted correctly. These numbers at first just tell you how much we predicted correctly in both categories, but there's a lot of more information behind this. And at the first glance, what I want to show is just this pie chart here, showing how the red area is all the songs that do not end up in the charts, which is a huge amount more. So if we would just guess that every song would not end up in the chart, we would probably also have about 99% there. Yes, but we would definitely not have 53 up at the top, but yeah, it's an important detail. So actually what we predicted correct of the hit songs is just half of this blue area, so a very, very small portion. To kind of get a feeling of this kind of thing, how the entire data set and so, what you usually use in machine learning to look at your results is a confusion matrix. And I'm going to show the confusion matrix for this data. So at the top you can see we used about 100,000 lines. And the true positives is the amount of correctly classified hit songs. The true negative is the amount of correctly classified non-hit songs. The false positive is falsely classified hit songs, and the falsely classified non-hit songs. So the top two are good. They are showing what we correctly classified either as a hit or as a non-hit. The bottom two ones, they're showing what we falsely correctly classified as a hit or a non-hit. And those two you want to have at 0. And you can also discuss which of them is worst. Depends a little on your what your data what you want to do with your classifier. But if we're looking at hit songs, like saying that this song will not be a hit and then it ends up being a hit might not be that bad. Except maybe if it's in a label and the label decides to like throw away that song because of the classifier, then it was bad. But otherwise, I think everyone would be very happy and the surprise would be even bigger. But saying that it will be a hit song and not be a hit means you maybe invested a lot of money and did a lot of stuff for something that was false. So that one is definitely, well, we considered it worse now and we're trying to get it down as much as possible. And here on the accuracies, you can see different multiplications of those numbers there to get the amount of correctly classified songs out of hit songs out of all songs that were hit songs, the 53%. Okay, so that were our results, but obviously it should be better. We want more than 53%. The fact is that an expert in the field of music that has been working for a lot of years might even be able himself to guess that good. So we have to be better than that. And how can we improve it? Well, I just want to show you one error or one fun thing where it went wrong. Was I ran the classifier on Wham last Christmas, between Christmas and New Year, and it was being played a lot on the radio, and the classification for it being in the next week on the chart was 88.34%. Next week I tried it again, it was not in the chart, and it was a 99.94% chance it would not be in the chart next week. So this is quite obvious because we're looking at the radio data and how much it's being streamed and stuff, and over Christmas it's being streamed a lot. So the classifier thought, okay, this song is growing like crazy, it's going to be a hit song. It's going to be in the charts next week as well. But no, it was completely wrong, because then Christmas was over and the song was not played anymore. So we learned from this that yes, we need to take into consideration like what's trending at the moment, social aspects. For example, if an artist is just died, almost always his songs get played more. If it's the anniversary of someone and stuff like that, just trends. And at the moment, that's not taken into consideration at all. That could definitely improve. And yeah, that's pretty much it, I think. Do anyone have any? Yeah.
means it will probably not be a hit.
Oh yeah, I could have
You should
mentioned
have
that. Yeah. Yeah, you're right. Uh,
What if like some musician has three different versions of the song? Like some hips version, like
Yeah.
some kind of acoustic, and some kind of, I don't know, heavy metal
Yeah.
arrangement, and he just wants to upload it,
yeah.
and then you give some score.
Like
It does not analyze the song, so you can analyze the airplay.
with the audio features. Yeah. But yeah, the limitation now is that it has to be played on the radio. So that's a limitation of this one right now. But it's also because of, it was part of the project to see how the radio influences. So, but if that artist would have all three songs playing on the radio, then he could run this against them and get a
But
comparison.
then it's what you said. Sometimes you like